Good afternoon, everyone. I am R. Ramashekar Patnaik and I welcome you all for today's webinar on stop guessing and start simulating. In this presentation, we are going to cover an introduction about us, what is FEA, how it works, industry challenges addressed by FEA, a hands-on demonstration of zip crane analysis, why SolidWorks Simulation, capabilities of SolidWorks Simulation, and a brief overview of 3D experience simulation. Before diving into the technical details, let me introduce myself. I am R. Ramashekar Patnaik. I have done my MTech from NIT Surat in Mechanical Engineering. Currently, I am working as a CA engineer at SolidWorks Solutions Limited. I have 2+ years of experience using SolidWorks Simulation and Abacus. I am a certified SolidWorks Simulation professional. I have worked on projects involving static, dynamic, thermal, buckling, and nonlinear. Coming to my company, Logical Solution Limited. Logical Solution Limited is established in the year 2000. We have grown significantly since our inception, becoming an authorized reseller of SolidWorks and achieving recognition as one of the top resellers in India, including SolidWorks 100% Sales Club and top Best Marketing Awards. So, Logical Solutions is committed to excellence in services through agility, transparency, employee inclusive, and customer-focused processes, providing end-to-end industrial experience in CAD, CAE, and CAM. Now coming to the topic, what is FEA or finite element analysis? And to understand FEA, let me introduce you to a simple problem. You want to measure the distance between your home to the mailbox, and you have a stick of known length. How will you do it? It's simple, right? You're going to place the stick in a continuous fashion and start from your home and reach till your mailbox, and you're going to multiply the number of times you have placed the stick, and you're going to multiply the number of times you place the stick with the length of the stick. You're going to get the distance from your home to the mailbox. This is simply is in a broader way an FEA. In FEA, you divide an object into set number of known pieces. You know the behavior of each piece. From that, you are going to understand the behavior of whole object. Let us understand some key terminologies of FEA. First one, element. An element is a fundamental building block in FEA. From our previous example, the stick is an element. Next one is node. A node is a point at which elements are connected. From our previous example, the start point and end point of the stick is node. Mesh. The collection of all elements and nodes is known as mesh. More the mesh density, better the FEA results, but longer is the time for computation. Like smaller the length of the stick, better the accuracy of measuring the length, and more is the time taken to measure. Degree of freedom. Why degree of freedom is important? We have taken a 2D case here while measuring the distance from the stick, from the home to mailbox. But what if the case is 3D? Then the whole problem will be different, right? So that's why we consider degree of freedom in FEA. The degree of freedom tells us the number of different ways a node can move or rotate. In the 3D analysis, each node typically has 3 degrees of freedom in translation and 3 degrees of freedom in rotation. So now let's discuss what are the steps involved in FEA. The first step in geometry is geometric buildup, where we import the geometry to be analyzed. And then next step is discretization or meshing. Meshing is what we already discussed, making a given object into set number of pieces. Next one is selecting the shape function, and then we form the elemental stiffness matrix. And then we are going to find the global stiffness matrix from each elemental stiffness matrix. Then we are going to form loading matrix of a given element. Then from that we are going to calculate the total loading matrix. and then you're going to formulate the equilibrium equation. In that equilibrium equation, you're going to implement the boundary conditions, and by solving the equilibrium equation, you are going to get the unknown nodal displacements and forces. So this is the typical procedure which undergoes beneath the FEA. So what are the phases in FEA? FEA is conducted in 3 phases: pre-processing, solution, and post-processing. In pre-processing, geometry cleanup is done and finite element mesh is developed. Material properties are applied. Boundary conditions are set. The solution phase involves solving the FEA model. And the final phase is the post-processing, in which quantities like displacement stresses are examined. Now coming to FEA applications. In aerospace and defense sector, FEA plays a vital role in ensuring the safety and performance of aircraft and defense systems. It simulates the stress on composite materials and analyzes aerodynamic loads, helping to create lighter, stronger, and more efficient designs. The automotive industry relies heavily on FEA for various applications. Crash simulation is a prime example, allowing manufacturers to improve vehicle safety. Additionally, FEA aids in thermal management of batteries in EV vehicles or electric vehicles, which is critical for their performance and longevity. FEA is instrumental in the design and construction of our infrastructure. It models load distribution in bridges, skyscrapers, foundations, ensuring structural integrity and preventing failures. FEA even extends into biomedical field. It simulates biomechanical interactions such as analysis of hip implants. The energy sector utilizes FEA to analyze fatigue in turbine blades, crucial for the efficiency and reliability of power generation. It also helps in assessing pipeline corrosion, preventing environmental disasters, and ensuring safe energy transportation. Finally, in consumer electronics, FEA is used to test heat dissipation in microchips, preventing overheating and improving device performance. It also plays a role in assessing smartphone drop resistance, leading to more durable products. So what is SolidWorks Simulation? SolidWorks Simulation is a powerful FEA tool within SolidWorks CAD software. It is an easy-to-use structural analysis tools to predict a product's real-world physical behavior by virtually testing CAD models. In essence, SolidWorks Simulation empowers engineers to predict real-world performance digitally, fostering innovation and efficiency in product development. So, coming to the steps in SolidWorks Simulation. The first step is to enable the SolidWorks Simulation add-in. Then we are going to create the new study, depending on the type of analysis you want to perform. The third step is to assign the material properties. And the fourth step is to apply the boundary conditions and to apply the loads. And then we define the connections between the parts. And then we are going to mesh the model, and then run the analysis, and then we get the results and we review the results. This is the typical overflow over which we are going to see next in coming session. So why SolidWorks Simulation? The biggest benefit is SolidWorks integration and associativity. That means you are working with your native geometry, and there is no potential headache like losing features or need for geometric fixes. You can also take advantage of SolidWorks powerful features like SolidWorks configuration and CAD defeaturing that may come especially handy for simulation. It is easy to learn and use. It is designer focused. We provide with you technical support, and we have extended community forums where you can reach out and connect with other people. We also offer you with suitable bundles which are cost effective. So now let's move on to a hands-on demonstration. Before moving on to hands-on demonstration on a jib crane, let us understand and answer a few questions. What is a jib crane? A jib crane is typically a overhead lifting device designed to move materials within a limited area. Now, what are the different parts in a jib crane? Coming to its parts, it consists of a column, a jib, a hoist, and a tie rod. Now, what are the different analyses will be carried on jib crane? This we will discuss in coming slides. Now, let's proceed further and let us view a video on jib crane. Hope my screen is visible.
Jib cranes, you see them in factories, workshops, even on those big cargo ships. They're like the trusty sidekicks of heavy lifting. They swing around, lift stuff up high, and make tough jobs a little easier. Basically, a jib crane is a simple crane with an arm, called a jib, that sticks out from a central support. Think of it like your arm, with the jib being your forearm. Now these cranes are strong, designed to handle a specific weight limit. That limit ain't just some random number. Engineers work that out carefully, considering the materials, the design, the whole 9 yards. It's like the crane's weightlifting class. It can handle a certain weight, but anything more is asking for trouble. Jib cranes are real workhorses, getting the job done day in and day out. But just like any piece of equipment, they've got their limits. Push them too far, and you're asking for trouble. The kind that can cost time, money, and even lives. Overloading a jib crane is like putting a hippopotamus on a seesaw designed for a kid. It's just too much weight, and something's gotta give. When you overload a crane, you put a whole lot of stress on its components. The jib, the hoist, the support structure. Imagine bending a paperclip back and forth. You can do it a few times, but eventually it snaps. That's metal fatigue, and it's a real danger when you overload a crane. The constant stress weakens the metal, making it more likely to fail, sometimes catastrophically. And it's not just the crane itself that's at risk. The load you're lifting can come crashing down, putting workers in harm's way. We're talking about serious injuries, even fatalities. That's why understanding weight limits and respecting them is crucial. Let's talk about a real-life example. A few years back, a construction site in Texas learned the hard way about overloading. They were using a jib crane to move heavy steel beams, pushing it beyond its limit. The pressure was too much for the crane to handle. The jib buckled, sending the beam crashing down on a group of workers below. Thankfully, no one was killed, but several workers were seriously injured. This accident is a stark reminder of what happens when safety takes a backseat to speed or convenience. Overloading a crane is like playing Russian roulette with people's lives. The aftermath of an accident like this is never pretty. Investigations, lawsuits, not to mention the human cost, it's a mess no one wants to deal with. Preventing these kinds of disasters starts with respect for the equipment and the weight limits it's designed for. Always check the crane's capacity. It's usually printed right on the side. If you're unsure about a load, ask someone who knows, a supervisor, an engineer, someone who's been trained to make those calls. Don't cut corners or try to push the limits. Yeah, it might take a little longer to do things by the book, but it's a whole lot better than dealing with an accident. Remember, safety isn't just about rules. It's about looking out for yourself and your fellow workers. At the end of the day, working smart and safe is what it's all about. Don't let a shortcut turn into a tragedy. Respect the crane, respect the load, and respect each other out there.
So, coming to our analysis, what are the different problems that may come in a crane? First thing we have observed is overloading, right? So what analysis we do to mitigate it? We do a static analysis. So what is static analysis? Let's go. The crane, the first thing we observe is its capacity. That is how much load can it sustain, right? So how the static analysis is going to help us to get the capacity of the load? Simple. First, we are going to load the crane with a operational load, and then we're gonna observe the deformation in the crane. If the deformation in the crane is below this what deformation that is being stated in standards, then we can assume the load which is applied is safe. So let me demonstrate you in SolidWorks simulation. So this is the SolidWorks simulation interface. Here we have a jib crane. I have already explained you the parts here: a column, a tie bar, and a jib. This is the hoist. So let me go through the simulation steps in general and static analysis in particular. In CAD model, you tend to include every part and detail which eventually get built. Simulation model is usually a subset of CAD model. So we do model preparation or geometry cleanup of CAD models to remove unwanted features and details like small holes, fillets. You then choose the type of analysis. So here I'm gonna choose the new study. Here, static study. I need static study, so I've chosen static study and I'm gonna click OK. So static study opened. Now I need to apply the material properties. So I'm going here and I'm going to apply the material properties. I'll click apply. We can choose the materials which are present in SolidWorks library. If you want a new material, then you can also add custom materials. For time being, I'm applying alloy steel. It is applied. You can see a green tick here, which means the material has been applied. Next part is interactions or connections. I'm going to give global interaction here. I'll keep it as bonded and I'll click OK. Next step, fixtures. I'll give fixed geometry. Here I see bolts where it will get fixed. So I'm gonna fix here. Like this, I'm gonna do for all the holes. And then I'll click OK. And then I'll click OK. Next step is applying the external loads. First, I'm gonna apply 110 load. I'll select the force here and I'll apply 110 load at the hoist. I'm selecting the face and I'm selecting the direction. I'm selecting the units to be SI unit. 110 is equivalent to 9810 newtons. Yep. And direction is reverse. So I have applied the load. Next step is meshing. Before meshing, I also want to apply gravity here. You can simply select gravity from here and it will show you the direction in which gravity has been applied. 9.81 and click OK. Next step is meshing. I want to apply the mesh control here. I'll select the faces. I want fine. I'll click OK. Next, I'm gonna create the mesh. Keep it fine. And coming to the parameters, it is blended curvature based mesh. And then I click OK. It's gonna do meshing. So we are doing static analysis. Here we have applied force and gravity. What is the agenda of doing static analysis here is we are gonna measure the deformation, and we are gonna compare the deformation with standards. And if the deformation is within the limits, then whatever load which we have applied is in safe limit. Meshing is going on.
So till now, what we have seen everything in a single user interface. Like, so most of the most of the members have used SolidWorks software. But if you want to do simulation, what we have to do, we have to go to another software. We have to import the solid geometry.
Yes.
So yeah, we have to apply the import as a step files, and we have to import as a step file, and we have to do the simulation. Again, if we want to make any changes in the geometry, maybe our simulation results are not good. So what we have to do, we have to make some changes, and we have to rerun it again. What we have to do, we have to make the changes in SolidWorks, and we have to re-import it again. And again, we have to do the simulation. But here with SolidWorks, with being in a single user interface, what you will get is, so the live updates. So what are the updates that we have done in SolidWorks CAD model? It is automatically updated in our simulation module also. So since there is no data loss and there is no repetition of job works has to be done. So it has to be in a single user interface and synchronized way. Yeah, you can continue, Srika.
Yes, I think here you can see if you want to make any changes, you can directly go to model and you can make changes and come back to the analysis with just one click. Okay, I think meshing is completed. You can see the mesh if you want to. You can see the mesh here and fixtures which we have applied. This is gravity and this is force. Okay, now I have already run this simulation, so let us review the results. Coming to the stress, it is telling we can modify these chart options here. We can make it scientific or floating. I want to select floating. I want just 2 decimal places. I can do that. Now you can see it is showing in float notation. It is showing 217.04, but where it's the maximum stress, it is showing me here. So this is the maximum stress which is localized, but if you see overall, it is not much of a stress, so there is no stress issue here. Let's move on to displacement. Displacement, it is showing 14.1 second. Again, I will change it to floating notation. You can see here from scientific, general to floating. I'll keep 2, then I'll click OK. We can see 14.23 mm is the deflection at the jib end. If we compare it with the standards, we'll get to know whether this is safe or not. I have checked it from my end and it seems to be safe. It was 20 mm something, but you can also do it from your end. All you need to do is download a standard and compare. This jib length is 4.3 meters and you need to multiply the allowable jib deflection. Let us suppose 1 tau, and you need to get the deflection, and then we need to compare it with our value, which is safe here. Now before moving on to the next analysis, let me go back to my PPT. So we have performed static analysis. Let us see what are the advantages of static analysis. Early design validation and enhanced design understanding, cost reduction and optimization of material usage, improved product quality and reliability, and risk mitigation. Now coming to the second problem, which is fatigue. The crane is frequently loaded and unloaded, which is cyclic loading. So let us suppose when the crane is loaded as condition as 1, and when it is unloaded, the condition to be 0. When the crane is subjected to loading, frequent loading and unloading, it will go like 0, 1, 0, 1 and so on. So there is cyclic loading which is going to happen. So we need to find the life of the crane. How many cycles can it sustain? How many cycles can it bear? For that, we are going to perform fatigue analysis. So let's go to fatigue analysis. In fatigue analysis, I have already applied the material, and in loading, if you see, I have created one event here. In event, I have selected the loading ratio to be 0 because the loading condition is from 0 to 1, and the study it is taking from static study, and I have applied it for 10,000 cycles. Now let us review the results. If you see the life, the minimum life it is showing is 1.95 e to the power of 5 cycles, which means it can take up to 1.95 e to the power of 5 number of cycles of loading and unloadings. That is what it means.
So here, fatigue will taken from the results of the static load. For before we carry to fatigue analysis, we have to do the static load. So static load means it's a one-time application that we have done the one time. If the repeated times we have done the if repeated task has been happened, however the life of the jib crane has to be analyzed with this fatigue analysis. So here we got a something like 1.9 into 10 power of 5, 1,95,000 cycles. So you can imagine, like in a day, you work your crane with the 100 times. You can imagine like 100 times. So that means 100 cycles you have worked for the you worked your crane. So that means if you divided by 1,95,000 means somewhere around 190 1,950 days, somewhere around you will get life of the cycle. Yeah, it will also indicate the wear and tear. For example, if you use for the 10,000 cycles or 20,000 cycles, how much damage percentage of the jib crane is happened. So all these things also we can analyze with this fatigue analysis. So as I told, the fatigue analysis will take in the results of the static analysis and give the by taking the values that what we have added in cyclic. So based on that, it will give the results for us.
Yes, Srinath. Okay. Now before moving on to the next analysis, let me go back to my PPT. So advantages of fatigue analysis. It is used for predicting structural lifespan, predicting catastrophic failures if happening, optimizing design for durability, reducing the maintenance cost, improving product reliability and safety. So what is the next problem that may come to crane? That is vibration. So whenever
yeah,
yes,
this
Srinivas.
maybe occur in different aspects. Maybe you may connect your motor to your jib crane. So if the motor resonance is matched to the first natural frequency of the this one jib crane, then there is a collapse. There might be a collapse is happen. Maybe some other vibrating objects also will be there within our what is work area. So if that vibrations match to the natural frequency of the jib crane, so it leads to a disaster problem, like problem to in our work area. So with that aspects, we have to consider for this resonance first natural frequency resonance also. So yeah, Shrikar, continue.
Yes. Also, like swaying, due to swaying, also there may be some excitation force which will be transferred to the crane, and this excitation, if it matches with the natural frequency of the crane, it is going to the resonance is going to happen, and we don't want resonance to be happening. If resonance happens, then the crane is going to vibrate in higher fashion, which is not desirable. So let us go to the simulation. In this simulation, I have taken the frequency analysis, or we call it as model analysis. In model analysis, I have applied the material properties and then component interactions and fixture condition which we have taken in static analysis and mesh controls. Now let us observe the results here. The first natural frequency comes out to be at 2.808 Hz. And the second natural frequency comes out to be 9.1391 Hz. So yes, it is critical to know the first natural frequency, but it is also critical to know how much mass participation is there. Mass participation tells us how much mass that is going to be taking part in that vibration. If there is very less mass which is going to participate in that, then we can consider that to be not very critical. But if there is more amount of mass that is going to be involved, then we consider it to be a critical voltage. Now let's see. Hello? Srinivas, can you mute? Yeah, thank you. Okay, here for first natural frequency, which came out to be 2.8 Hz, we can see that mass participation factor is low, which is 0.11 in the direction of jet. If we see the second model shape, then which is at 9.1391 Hz, the mass participation factor is 0.56501, which is significant. So we will not consider the first natural frequency to be critical. We consider second natural frequencies to be critical. And let us also observe the mode shape. If the type of mode shape is, we need to observe the type of mode shape also, whether it is critical or not. Mode shape basically tells how the vibration will look like. We can see here the vibration is in this manner, which can be considered as critical. So second model shape is going to be critical, which is at 9.1391 Hz. So now coming back to PPT, what are the advantages of frequency analysis? It helps in resonance prevention, vibration control, predicting dynamic behavior, and in noise reduction. So what is another problem that may come to crane? That is earthquake. In earthquake prone areas, chances are there earthquake will happen. If earthquake happens, the crane must sustain. For this, we perform response spectrum analysis. Let me go to the SolidWorks interface. So I have taken an earthquake which happened in California in 1997. I have loaded the base excitation. I have converted the data of acceleration versus time graph into frequency domain. And I have obtained the frequency curve, which looks like this. Okay. This is the base excitation I have given, and direction is also important. What if the earthquake occurs such that the direction of excitation is in positive x direction? Let us view the displacement. It gives us the maximum displacement that is going to happen. The maximum displacement is 3.799 mm in positive y direction. Okay, that is somewhat okay for me. But what if I apply the excitation, or if the earthquakes happen such a way that excitation happens in a perpendicular or in z direction? Then if we observe the results, the displacement is going to be 15 mm. Let me edit the chart options. The displacement comes out to be 15 mm, which is quite high. And also it is going to occur in this fashion, which is perpendicular to the grain. The load may fall if 15 mm of deflection may happen. So this is one critical issue. So let me go back to PPT now. So what are the advantages of response spectrum? We have conducted response spectrum analysis here, right? Response spectrum is an efficient analysis for dynamic events. It is used for predicting peak responses. It is used for seismic analysis like earthquakes and shock analysis. It simplifies the complex dynamic problems. Now, we have performed static analysis and fatigue analysis. So what are those? Static analysis of a chip crane is a fundamental step in ensuring structural integrity and safe operation. Static step involves determining stresses, deformation, and factor of safety. Through static step, we compare the deformations with standards and determine the safe operation. Performing a fatigue step in crane gives us information about the life of the crane. This is the hand calculation which I have done. Now coming to dynamics. We have performed two dynamic analysis. One is model analysis and second one is response spectrum analysis. In model analysis involves extracting the natural frequencies of the body. We have extracted the natural frequencies. We have also extracted the mode shapes and mass participation. The second one is response spectrum. In response spectrum, we load the excitation data like earthquake in frequency domain and observe the deflection. The deflection will be peak deflection, peak response, which we have observed. Now coming to the capabilities of SolidWorks. First one is static. We have already gone through static analysis. I hope I don't have to cover it again, but basically we will, in static analysis, we are going to see deflection, stresses, and factor of safety. The second one is fatigue. In fatigue, we observe the life of the model. Third one is motion, time-based motion analysis. Time-based motion analysis looks at the rigid body kinematics of moving assembly. What the time-based motion analysis in simulation does is, it extends the CAD capabilities with some actual numbers. You can find the forces and values of accelerations, velocities, and so on, and use that to size motors and actuators. So time-based motion analysis shows the model response to time-based changes. Next step, 2D simplification. In cases of plane strain, plane stress, and axis symmetry, 3D simulation problem can be reduced to 2D problems. We call it 2D simplification. In this way, we can reduce the computational resources. Frequencies. We have done the frequency analysis, in which we have extracted the mode shapes and natural frequencies. And third one is, and the sixth one is buckling. Buckling is a failure, therefore it is quite critical. When a slender bar is subjected to compressive force, at some point it is going to see it's going to show us some excessive sideways deformation. This phenomena is known as buckling. Buckling is relevant if you have slender bars subjected to compressive loading. Can anyone tell me why we haven't performed buckling analysis for this crane? Okay, let me answer. We can see one slender bar here, which is here, but we have not conducted buckling analysis for it. Why? Simply because there is no compressive load here. There is only tension in this bar. If this tie rod was existing downward, then it may have been subjected to compressive load. Then we should have considered the buckling also. So that is the reason why we have not considered the buckling case here. Okay, coming back to PPT. Next one is thermal analysis. Thermal analysis is relevant when you have a heat source and want to know the temperature distribution. A thermal study can be steady state or transient. We have additional features like thermostat and thermal contact resistance. Sometimes, especially in high-tech industries, you have epoxy or glue in between parts, right? These are typically very thin, so you do not want to model them. You don't want to model them and mesh them. What we can do is we can just use this thermal contact resistance and just model the effect instead of directly modeling the epoxy resin, which is of thin layer. That is where thermal resistance comes into play. The next step is optimization. Every engineering is finding for optimal design, right? In optimization, you have design studies and topology. In design studies, you can define variables and constraints and goals and get the optimal solution. Then we have topology. We start with the design space and program comes up with the optimized shape for the given conditions. Next step, submodeling. Submodeling is a FEA technique to obtain more accurate results in specific region of larger model. In this, you first define a global mesh, which is post mesh, and then run the model. And then you select the submodel in the global space or global model, and you fine mesh it to capture the detailed stress or strain distribution. As you can see here, I've taken the global mesh, post mesh for this model, and I have only submodeled this part, and I have fine meshed it, and I have got the stress or strain distribution. Next step, event-based motion analysis. Event-based motion analysis extends the capabilities of time-based motion analysis. It has triggers, tasks, and actions. In some assemblies, like assembly line in factory, there are certain tasks that must be completed before other tasks. Event-based motion analysis helps you to capture such behaviors. Next step is pressure visual. SolidWorks Simulation provides specialized pressure visual design study time. This allows you to combine the results of multiple static studies, which is essential for evaluating pressure visuals. This feature is useful for complying with design codes that require the combination of various loads. Next step is drop test. Drop test is used to evaluate the structural integrity of the product when subjected to impact, such as when it is dropped from some height on hard surface. This is crucial for ensuring product durability and reliability. You can define parameters like drop height, impact velocity, gravity, impact surface orientation, target stiffness. Drop test is carried out using explicit dynamic analysis. Next step is linear dynamic analysis. Unlike static analysis, which assumes constant loads, linear dynamic analysis deals with loads with change over time. There are 4 types of linear dynamic analysis in SolidWorks: model, time history, harmonic analysis, random vibration, and response spectrum. Model time history calculates the response of a structure over a period of time to time-dependent load. Harmonic analysis determines the steady-state response of the structure to harmonic loads or excitation. Random vibration predicts response of a structure to random vibrations. Response spectrum analysis is used to analyze its peak response of structures to transient, in earthquakes. Non-linear analysis. Linear analysis assumes some linear material behavior and small deformations and constant boundary conditions. These are the assumptions which we'll take in linear analysis. But when there arises case of non-linearity, like material non-linearity, contact non-linearity, or geometry non-linearity. What is material non-linearity? Material non-linearity is a case where when there is no, if we take stress and strain curve, if it is linear, up to proportionality limit it is linear for steel, right? But if you go beyond yield strength, then it is going to be non-linear. If you take plastics, the relation between stress and strain, it is going to be non-linear from the beginning. For such cases, you need to perform non-linear analysis. And coming to non-linearity in geometry, if there is a deformation in a geometry which is beyond some certain limit, then also you need to consider non-linear analysis, because there will be change in stiffness matrix. And there is non-linearity due to contact condition, which you can see here. If there is changing in contact conditions, like sometime it is coming in contact and sometime it is not coming in contact, then also you need to perform non-linear dynamic analysis. Composite analysis. SolidWorks Premium offers advanced capabilities to composite analysis. It allows you to define and analyze symmetric and non-symmetric, unsymmetric composite layers. It also allows you with failure criteria to define some failure criteria like Desai O and Desai Ill. These criteria help you to predict failure by considering factors like fiber delamination and fracture. Now, non-linear buckling. We have studied is the linear buckling, but when does we use non-linear buckling? To get that, first we need to understand that linear buckling does not say how the distribution of loads looks like what are the actual displacement and stresses. To know that info, you need to, and to get a more accurate picture of the behavior, you need to go to non-linear buckling analysis. A linear buckling analysis is easy to set up, but it just gives the information in terms of buckling load and shape. But to capture the complete behavior, you need to go to non-linear buckling analysis. Now, these are the capabilities of SolidWorks simulation.
So till now we have seen desktop solutions. So where SolidWorks was connected to the simulation and we have done the simulation. So we have a couple of times we have a requirement like so we required a cloud kind of solution, the cloud data management kind of cloud simulations solutions, maybe on a certain project and maybe on a certain period. So SolidWorks is a desktop simulation and it's a lifetime license we have. Sometimes we may require as a project level, as a time period level kind of packages also. So that's why SolidWorks come up with a one more package like 3D experience, 3D experience works. So where we have all the capabilities, it includes SolidWorks, Katia, Simulia, Delmia, Via and Excite for covering all the design and engineering capabilities and simulation requirements and manufacturing, production, governance and marketing sales. So in that, simulation is also one of the part with the roles of Simulia, where you can purchase what you want. Maybe some may required only static simulation and some may required only frequency simulation. So each and every one has a different requirements. So based on that, based on the certain period, if you want on a certain period, so you can go with this 3D experience role where you can purchase what you want. So you no need to purchase everything. You can purchase what you want and you can run it for how much time you require. So the licensing flexibility is there with this 3D experience. You can continue, Srika.
Yes. Yes, Srinivas, thank you for that additional info we needed. Okay, so that is about what SolidWorks is, and let's move on to its capabilities and different roles that are present in SolidWorks. In Simulia, we have structures, fluids, plastics, electromagnetics, and motion. we can also do simulation review. In structures, we do structural analysis. In fluids, we have CFD. We have injection molding analysis we can do using plastics. We have electromagnetics and motion. So coming to the roles which we are offering. In 3D experience, we have structural designer, structural engineer, structural performance engineer, durability performance engineer, structural mechanics engineer, and durability and mechanics engineer. We will see what are the capabilities in the coming slide. We also have fluid dynamics engineer and electromagnetics engineer. In plastics, we have plastic injection engineer. In motion, we have 3D motion creator. And for simulation review, we have simulation collaborator. So coming to the structures, we have structural designer. In structural designer, we have linear, static, frequency, thermal, and buckling. Structural engineer will have all the roles which are present, all the capabilities which are present in structural designer, and including that, we have harmonic response, model dynamic, and advanced meshing features. Structural performance engineer will have all the capabilities of structural engineer, and it will have nonlinear static, thermal structural, dynamic implicit, and advanced connectors and contacts. In structural performance engineer, we have durability performance engineer also. In durability performance engineer, you will have all the roles of all the capabilities of structural performance engineer, including that you will have fitting. And then we have structural mechanics engineer. Structural mechanics engineer will have all the capabilities of structural performance engineer, including that we'll have dynamic explicit, quasi-static explicit, complex frequency, random vibration. And if you go to durability and mechanics engineer, it will contain all the capabilities of structural and mechanics engineer, and with that we'll have fatigue. So wherever durability is coming, fatigue will come. So this is about the different roles and their capabilities in 3D Simulia.